we need to know how to do some stoichiometry calculations on solutions, because this does come up in the lab. You might want to know how many grams of something you need to react to get a certain amount of grams of product if you're weighing solids. But if you're working with things that are already dissolved and in solution, you might want to know, well, what volume of this particular solution do I need to do the reaction with either this volume or this amount of grams. So the reaction itself is based on a molar ratio. Those balanced equations with these coefficients, those refer to the moles. And so to get between volume of solution and moles, the useful concentration that we can use is molarity. That's the relationship between moles and liters. You can get from liters of solution to moles of the solute. Okay, so what if you are reacting some acid and some base? Sulfuric acid and sodium hydroxide, you want to react them so that they are even and you neutralize the solution. So we are starting with a volume of substance A, in this case is sodium hydroxide. We have our volume of solution A. We're going to use the molarity to figure out our moles of sodium hydroxide, our moles of A. Then we're going to use the coefficients of the reaction to get to moles of sulfuric acid. And then we're going to use this molarity to get to the volume of sulfuric acid that we need. So this is with what we're starting with, our amount of known substance. Sodium hydroxide in this case is our known substance because we know both the concentration and the volume. This one is partly unknown. We know the concentration but not the volume. The volume of sulfuric acid is our unknown. So we're starting here. And our relationship between moles and volume, the 1.75 molar is 1.75 moles per liter. Our volume is in milliliters, which a lot of times happens in labs. You don't have liters and liters of your substances. You might just have some milliliters. So let's go ahead and convert this to liters. So now we'll have liters of our sodium hydroxide solution. Way less than 1 liter is what we have. And then each of our liters of sodium hydroxide has 1.75 moles of sodium hydroxide in it. Now we're at this point, we need our molar ratio to start talking about sulfuric acid instead. We have 2 moles of sodium hydroxide on the bottom to cancel and start talking about sulfuric acid. Now we can use the molarity to convert from moles of sulfuric acid to liters of sulfuric acid solution. If we wanted the volume of sulfuric acid solution, we could stop here. We do want it in milliliters, so let's just put one more step here. And we end up with 30.0 milliliters of sulfuric acid solution. Our original volume had 4 significant digits, but these concentrations are only known to 3, so I rounded it down to 3. So this next one's a little bit different. We want to know how many grams of sodium carbonate would react with a certain volume of solution. So we're looking for grams of sodium carbonate. So once we know the moles of sodium carbonate, we're going to use the molar mass rather than concentration because we don't have the sodium carbonate in solution. What we are starting off with is the volume of a solution with known concentration. So it's like we're starting at this part of the roadmap. We'll use the molarity concentration to get to moles of hydrochloric acid, and then we'll use the coefficients of the reaction to get to moles of sodium carbonate, and we'll need to find the molar mass. Alright, I've gotten a little bit more room here and calculated the molar mass of sodium carbonate. So we're starting with a volume of solution, 31.5 milliliters of hydrochloric acid. And then we know the relationship between moles and liters. So let's go ahead and get this milliliters to be liters. So now we have liters of hydrochloric acid solution. Now we can convert to moles. So after this step, we have moles of hydrochloric acid. Now we want to start talking about sodium carbonate. So we'll use those coefficients. 2 moles of hydrochloric acid will react with 1 mole of sodium carbonate. So at this step we would have moles of sodium carbonate. And now if we use the molar mass, we can get grams of sodium carbonate. So here we have our milliliters canceling, our liters of hydrochloric acid solution canceling, our moles of hydrochloric acid solution canceling, our moles of sodium carbonate canceling, and we end up with 3.89 grams of sodium carbonate. So if you wanted to make sure you had enough sodium carbonate to react with all of your hydrochloric acid, this is how much you would need. So in this problem, we're back to asking for volume rather than grams. And then I just saw this concentration, and it doesn't hurt if you ever see a concentration to write out the relationship for what that means, because if you're given a concentration in a problem, you'll probably have to use it as a conversion factor. So writing out the relationship can help there. So here we are not starting with a volume. Instead of being told we have so many milliliters of this concentration of solution, we're kind of like given a head start. We would use the volume and the concentration to figure out how many moles of sulfuric acid we have. Let me see if I can illustrate that. So we're already starting out one step in. Instead of having to use the volume and the molarity to get to the moles, we are already starting at the moles. So all we have to do is use the coefficients to get to moles, and then the concentration of sodium hydroxide to get to the volume that we're looking for. So we are already talking about moles of sulfuric acid. We can use the coefficients to get to moles of sodium hydroxide right here in the next step. So now we have moles of sodium hydroxide. We can use our molarity to figure out the volume. And this ends up being 6 liters of sodium hydroxide solution. I put 6.00 just to show that everything in this calculation had at least 3 significant digits. So here is another problem that combines a volume of a solution of known concentration and a mass of solid, because this particular reaction we are starting with solid zinc, and we want to make sure we have enough hydrochloric acid in our hydrochloric acid solution to completely react with that. So we are starting with grams of zinc, and we'll use the molar mass to get to moles of zinc. Then we'll use the coefficients to get to the moles of hydrochloric acid, and then we can use the molarity concentration to figure out what volume of that solution is needed. So since we want moles of zinc, we're going to need the molar mass here. And eventually we're going to need to use this concentration as a relationship to get from moles of hydrochloric acid to liters of that solution. All right, we'll start off with our mass of zinc. Use the molar mass to convert that to moles of zinc. And then use the molar ratio to stop talking about zinc and start talking about hydrochloric acid. So at this point we'll have moles of hydrochloric acid. Now we can use our molar concentration, our molarity. So at this point we will be talking about liters of hydrochloric acid solution. And it comes out to 0.0986 liters of hydrochloric acid solution. It just asked for the volume, so this would be a valid answer in liters. If you prefer to report milliliters, this is equivalent to 98.6 milliliters of our hydrochloric acid solution. So up above we had this roadmap that led from volume of one solution to volume of another. If we knew our volume and our concentration of solution A, and we know our concentration of solution B, then we can get all the way across here. A titration is a way of finding out the concentration of a solution. So what if we don't know the concentration of our solution? That's what we want to know. But we do know the volume. So it's kind of like we're filling in this blank over here. So if we know the volume of solution B, and we can use a different solution, volume and known concentration, to figure out the moles of B, then we can use these two pieces of information to figure out the molarity of B. So it's kind of like there's a break in this chain, and we approach from one direction, we approach from the other direction, and we combine this information to get our unknown concentration. Our unknown concentration is sulfuric acid. So this is our B. Our sulfuric acid has an unknown concentration. But you do know the volume. See how you know the volume of B, you just don't know the concentration. What you do know, both the volume and the concentration of, is a sodium hydroxide solution. So that's what we're going to start with. That's our A. We'll get our moles of sulfuric acid from that. So to get the molarity of our sulfuric acid solution, we need to know the moles of sulfuric acid and the liters of solution. So we know the volume of solution. We know that it's 15.00 milliliters. So this we're just going to use a metric conversion to get to liters. For this numerator, the moles of sulfuric acid, we're going to use the other substance that we reacted it with. We're going to calculate, using our sodium hydroxide, how many moles of sulfuric acid reacted. Alright, so we're starting with our volume of known sodium hydroxide solution. And it's in milliliters. Again, titrations are usually not done on several liters scale. So we have milliliters. We'll convert that to liters, just because the concentration of sodium hydroxide gives the relationship between moles and liters. So now that we have liters, we can use that concentration to get moles of sodium hydroxide. So we're sort of at this step, and now we need the coefficients, the molar ratio, to get moles of our other substance, sulfuric acid. I've kind of run out of room, but the answer to this ends up being 0.009396 moles of sulfuric acid. So let's go ahead and start putting together this fraction. So our moles of sulfuric acid, let's put that in the numerator. Then we need our liters of sulfuric acid solution. We know the milliliters, 15.00 milliliters. We divide that by 1,000 and we get 0.01500 liters. I'm just showing that we have measured the volume fairly carefully. We have 4 significant digits in our volume. It's not just 0.015 liters, it's 0.01500 liters. A lot of times you'll notice these concentrations are known fairly precisely. 4 significant digits here. This volume and this volume we're being very careful with. We go 2 past the decimal. So when you do a titration in lab, it's usually something that you are taking a lot of care in and measuring it very carefully. So we'll keep our 4 significant digits to show that, and it ends up being 0.6264 moles per liter, which we can also express with a capital M. So here is the concentration of our sulfuric acid solution. Alright, I had to scroll up and get enough room to do this last problem. We are looking for the concentration of a hydrochloric acid solution. We know the volume, so we need to divide moles of hydrochloric acid by liters of solution. The liters of solution we're going to get from the 25 milliliters. So we know the volume of hydrochloric acid solution, it's 0.02500 liters. The moles of hydrochloric acid we don't know, but that's why we reacted it with sodium hydroxide. We're going to get that amount from our known sodium hydroxide solution. Let's do that here. We have the concentration of sodium hydroxide known as far as how many moles are in a liter of solution. So let's go ahead and convert the milliliters to liters. Now that we have the liters of sodium hydroxide, we can use the molarity concentration to convert that volume into moles. Then we can use the molar ratio in our reaction to convert from moles of sodium hydroxide to moles of hydrochloric acid. And now we know our moles of hydrochloric acid to 4 significant digits. So now we have both of our numbers that we wanted to calculate the molarity. We have calculated that we have 0.006260 moles of hydrochloric acid in a volume of 0.02500 liters of solution. And that comes out to be 0.2504 moles per liter, or you can also write it 0.2504 molar hydrochloric acid.